So it started to process the image there. Okay, so you will see here is the training progress. So that's why the last parameter here just showing you how to plot that one. We asked the computer to plot and show to us the training progress. Okay. Okay, there we go. So the training progress can be interpret in terms of accuracy, or you can also interpret as loss. It should be similar because accuracy is going to 100 and the loss should be going to 0. Okay, there's the same things. Okay, as you can see there, you can again the validation accuracy, the last one is 99.92%. Of course, a Minis data set is not very challenging, okay, because even before CNN becomes so popular, Minis data set have been used for testing with the shallow neural network, and I think there's one example in how actually the MATLAB show implementing the shallow neural network using this Minis data set, and I think you can find out that the accuracy can go up to 90%. So that's why if you talk about CNN, it will be more better, which is 99. It's almost 100%. And the things that I forget to discuss in this parameter again in the option there is the maximum epoch, because I set my maximum epoch is only 4, so that's why it stopped at the 4 there. Even it can go more and more because they find out now the stop criteria is not the overfitting. It's because it's already achieved the epoch equal to 4. Again, remember that we have many criteria to stop. One is if the epoch is already achieved at the maximum epoch, you stop. That is the final stop. But in between that, if you find out there is a underfitting, or sorry, there is a overfitting happen, by using the validation accuracy as a indicator, and comparing the validation accuracy and the training accuracy, if you find out that the validation accuracy drop and actually the the training accuracy is still going up, then overfitting happen, you will stop also at that time. So there's a two way to stop there, but in this case we stop at the maximum epoch, which is number 4. And you can see the dot there. The dot there is show you the validation frequency. You can see this one again, we already set there. Okay, validation accuracy equal to 30 iteration. So that's why for each 30 iteration there's one validation, another validation at 60, and then another validation at 90. So that is validation. You don't have to validate for each iteration, but you can set there, so it will make the code going faster, because if you put too many validation, it become more slow. And then the rest is just I'm using my computer because my lab support my GPU, so that's why I'm using the single GPU. If your computer don't support the GPU, then it will write here a CPU. And then what else? The maximum iteration is 232. So how come the 232? And then okay, you can see iteration per epoch is 58. Why 58? So again, my calculator is a little bit slow there. Okay, our training size is 7,500. And then again, by default, our mini batch size is 1 to 8. So if you divide with 1 to 8, then what you get is 58 something. So if you round the number, is 58. So that's why one epoch you have a 58 iteration, and each iteration you update the window. Mean that for one epoch you update 58 times. Okay, so meaning that you have 7,500 sample, and then you divide into 58 mini batch. So each batch the batch size is 128 per sample. So that's why for each batch you update the W. So meaning that you have a 58 iteration, and one epoch you update 58 times the W and the bias. So that's why iteration per epoch is 58. So that's how you can calculate that. Okay, so that's how you can do that. So that's it. So once you finish your training, so then you already get the net there, which is represent your train your learned architecture CNN net. Then you can use it for classification. Okay, it's already trained there, the net. Then the last step is to apply this one, which is to do some testing. But again, like I said, in this MATLAB, I'm not agree with this MATLAB example. As you can see, when they want to predict the accuracy of the system, they are using the validation data, which is validation have been used inside this training, which is very biased approach in representing the performance of the system. Okay, so that's why if you execute this one, okay, once you execute this one, run section, then you get this 99 from 92, which is similar to this one. Of course, it's similar because you are using the validation data to do testing. So that's why you get the testing accuracy 99.92. So that is actually a biased way to do. Okay, this one is just, I just show you some display of the testing your net there to classify image inside this 1000 data. Then you can run it. Okay, if you run it, it will show. It's just display the numbers. Okay, and then it will show the classify. Okay, you can see the output there in this common window. Okay, the actual output is 7, the predicted output is 5, 9. So if the same number is correct, so I don't know whether you can see the one that is incorrect, because if the predicted and the actual is similar, then the means that is correctly identified or correctly classified. Okay. So again, if you talk about the good way to do this one instead of bias like this, means that you are applying the validation data as for testing. So you must write at the beginnings there. Okay, here for me, let's we set the training data is 700 per classes. Okay, and then the rest will become validation. What I do is actually, one way to make it is not biased is you separate your validation data, the remaining validation data, into testing data. Means that sorry, okay, what you can do is that testing. So I declare another data set which is called testing data set. So I just call it IMDS test. Okay, or testing, IMDS testing. It's better test data, so IMDS test. So what I do is this: after I execute this line, meaning that 700 will go, time 10 will go to this thing. So the remaining 300 times 10 will go to this thing. So then what I do, you can split this one again, the validation into testing. You put here. Okay, you put here, and then you put here, because the remaining validation data is 300. So how about just put 150, meaning that now you split your original validation data into new validation data where 150, but the remaining 150 times 10 will go into this test data. So now your validation data, you will have training data which is 700 times 10, validation data 150 times 10, and test data which is 150 times 10. So I just run this section back, and then the rest is same. Okay, the rest is same. So but you need to train again, because you have a new training data and new validation data, so I need to train again. So I execute this one. Okay, we execute again. Okay, 99.96% and 99.96%. Is it a drop, the accuracy? No, it's increased 99 because the previous one is 99.92. Okay, doesn't matter that one. And then during the testing, this one you replace with testing. Okay, test. Okay, IMDS test. So this one IMDS test. So then the accuracy here will represent the accuracy of your testing accuracy. So you can see if I run this section, then I get 99.47%, which is not similar to our validation data, our validation accuracy, which is 99.96%. Okay, so that's how you can do to make sure that it's a proper way to do that. Okay, we have finished one. Okay, we have finished that, how the section that how actually we build the network from scratch.